So same introduction as before. We asked a very difficult question to Markus, who kindly agreed to try to attack this problem for our discussion. And yeah, I'm not so sure I get the entire meaning of the title, but you will clarify QFT and PeV colliders.
I thought I'm in a Latin country. I mean, ad astra just means to the stars, right? So, okay. Yes, I was given an impossible task, which is to talk about quantum field theory and PeV colliders. And of course, I failed. And I realized that the failure will be much worse for me than for you, because I will be very embarrassed and so on. And then going to the other talks in this conference, it just increased my sense of imposter syndrome. I mean, I'm incredibly impressed by all of the amazing hard work that's being done on future colliders, and I find it really, truly inspiring. And I think compared to that, I don't know that I have very much to say. So what I decided to do is I'm offloading part of this onto you. So what I have is 15 slides. Okay, that's not very much. And so if nobody interrupts me, argues with me, or asks me questions, we'll be done pretty quickly. All right, so just know that. I think it's okay. I've never really been to a talk where anybody said, that was a great talk, it was just too short. All right, okay, so those are the rules, all right, and I really tried to do the best I can. Yeah, I'm even talking about things that also, I should say, another disclaimer is that I'm talking about things that I don't know very well, so it's extremely possible, at least in the first part of the talk, I'm talking about things I don't know well. And I could just be saying something really stupid, okay? So, but I'm gonna do it anyway, because I'm beyond the reach of justice. All right, so I wanna start off by head-on talking about, in the last talk we've heard this referenced also, the nightmare scenario, okay? What is this nightmare scenario? I keep hearing about it, right? What if experiments just keep confirming the standard model? Yeah, we have a couple of anomalies, but they could definitely go away. They could just go away, like past anomalies have gone away. There's no clear indication of where we should look for new physics, okay? The last significant discovery was in 1998. What was that? Anybody know? The accelerating expansion of the universe, okay? Because I'm not talking about particle physics here, I'm talking about cosmology. Everything I said here is something you could say about cosmology. Have you ever heard anybody in cosmology talk about the nightmare scenario? I haven't. So what's going on, okay? So that was my setup. That was meant to be my joke slide. So you see how that went, okay? Now we're 2 out of 15 slides in. So you see how this is gonna go, right? All right? So like I said, argue with me, okay? I won't use this big stick on you, I promise, okay? So that's not what I think. That's not what I think at all, okay? And so in the past, when I tried this out on people, they also misunderstood that I was trying to say something that I'm not. So I'm just gonna be very explicit. What do I actually think, okay? So this is the last thing I'm gonna say about cosmology. This is not a talk about cosmology, but I think that particle physics and cosmology both have this amazing standard model that has incredibly unprecedented predictive power, right? And I didn't say it here, but there's no really clear indication of any anomaly. Yeah, there's some interesting anomalies in cosmology, there's some interesting anomalies in particle physics, but we've seen that script before, right? So that they're both incredible. Okay, so now I'm not going to talk about cosmology anymore. This is what I think about particle physics, okay? Our task as theorists and experimentalists is to leverage this incredible achievement, right? And to extend our understanding into regimes where the standard model has not been tested, okay? Now, it's weird that I even have to say this in a sense, right? Because doesn't this, when you learned what science was in grade school, it was something like this, I think, all right? But now somehow, when we're in particle physics, we think somehow it should be different, okay? We should be, there's this movie, which everybody I think should see, called 7 Days in 1 Year. It's a Soviet movie made during the Khrushchev times, and there was a sort of brief opening up. It's about nuclear physicists, so it's kind of cool. And anyway, they make jokes about communism in this movie, okay, which is why it's kind of interesting. Anyway, one of them is that these nuclear physicists are saying that their 5-year plan is to discover a new particle every year, right? So anyway, okay. That was my second joke, so let's see how that went. All right, so now what I want to say is that calculating in the standard model is challenging, and challenging is an understatement. We don't know how to do it, okay? And the standard model is not boring, okay? And that is the outline of my talk. So these last 2 points are what I'm going to talk about, okay? All right, okay. All right, so what can we calculate? What can we calculate, all right? So first of all, let's take a very, very broad view and realize that not just in the future, but already right now, high energy collider experiments can measure far, far more than we can ever hope to compute, right? Okay, so, and this is just a, phase space, okay? Because the number of particles that we produce is somehow proportional to the energy that we have, and somehow if you have n particles, you can make, n factorial type observables, so, this is just only gonna get worse, right? We're going to go better, worse, I don't know, more, okay? And what I want to claim is that calculating, okay, getting any kind of handle on these many observables is a problem of separation of scales, all right? And let me explain what I mean. So we're familiar with this in the case of QCD, right? In QCD, a Hadron Collider at the LHC or even before, we produce lots and lots of hadrons, okay? But we're able to make precise predictions, even though we don't understand hadrons very well, right? We're able to make precise predictions because we can see these as an underlying hard process followed by showering and hadronization, right? But now, if we go to even higher energies, right? If we're going to super high energies where we have, PeV or even, the muon collider is, I think, sort of the 10, 10-ish TeV muon colliders, the first place where we're seeing the face of this emerging, but we're going to have the same effects for electroweak interactions, right? And so what I'm going to be talking about the next few slides is that I think this is not as understood as we sometimes think it is, okay? And so I'm going to try to say that, and like I said, this is not my subject, so it could be wrong. Somebody can tell me, no, we already understand all of this, all right? So here's a simple electroweak process that we're very interested in at a muon collider, for example, right? You produce a Higgs by a vector boson fusion, right? But now, if we're really at energies much larger than the electroweak scale, right, then we can think of all of these particles, even the W's, Z's, and Higgses, as being nearly massless. And so we have processes like this, okay? So let's remind ourselves what is showering, okay? So even though we don't have hadrons or anything, the point is that we can have diagrams where we have some particles that are off shell, but they're not very off shell, okay? They're sort of off shell by of order their mass, but that mass is way, way below the collision energy. So there's some hard part of the process inside here, okay? But instead of all the particles being exactly on shell in the hard process, they're a little bit off shell, and so they can just sort of keep going, right? And something that's been understood for a long time is that these kinds of diagrams, although they're suppressed by additional powers of the couplings, they're enhanced by powers of the logs of the ratios of the scales, right? Namely the collider energy scale divided by the masses of the particles, okay? So at say a PeV collider, right, in a typical electroweak event, you would make maybe 10 to the 3, 10 to the 4 WZs and Higgses, all right? And so it is completely hopeless to say that somehow you're going to predict the distributions of all of these things, right? So what is it that we can compute? What is it that we do compute, right? We use this idea called factorization, right? Which is familiar from QCD. And the idea is that we focus, so out of these sort of exponentially large number of things that we can do, we just sort of sum over all, we do something semi-inclusive, right? We just sum over a bunch of hadrons, right? And have some hard underlying process. So for example, a high PTW, a very large invariant mass for a lepton pair, plus any number of hadrons, okay? But we don't typically inquire too much about these. Of course, then we can have jets, so we become more and more exclusive, and we try to compute as many things as we can, try to predict as many things as we can to compare with theory, okay? And so we have these, to make these things precise, we have these factorization theorems, and this is not really precise. I'm not just trying to give the idea, but the idea is that we have an underlying hard process which involves some partons, which are here would be quarks and gluons, right? And then we have some soft part, which is factorized into these parton distribution functions, which tell us how much, what is the probability to find a certain parton in a certain hadron, here proton 1 and proton 2, x is the energy fraction. So this is not exactly right, but gives the idea, okay? So this is all very standard, okay? I do want to say that I think it's an interesting question to ask whether there are other approaches, okay? Because we have this incredibly rich amount of data, okay? Are there other things that we could do with it? Okay, beyond what we already know how to do. There's one example which I think is quite interesting, which are these energy correlators. I'm not really wasn't planning to really say much about them, except that I think it is an interesting approach. Basically, the idea is that a sort of Lego plot that you would see from a calorimeter is an IR-safe quantity, okay? And so you can actually sort of predict the distribution, moments of the distribution of energy in a Lego plot. That is a quantity you can compute, and it's being used. It actually goes back to 1978, but it was revived more recently by Hoffman and Maldacena, okay? Another kind of approach that some people at least are talking about is maybe we can just simulate the whole thing, right? Quantum computers might solve everything for us. And sure, why not? I think that if we have something, I think that's something like an oracle, and it would certainly help. It would certainly help to have that, but it's not something that we should, you know, pin our hopes on. I think that this traditional factorization approach is really important, even if it isn't the only game in town, okay? It's intuitive, right? I mean, so there's a sort of the original Feynman-Parton model intuition underlying this. You have a hard collision, and then later the hadronization happens, and so on. I think, you know, more, I don't know, more scientifically or something, it's Wilsonian. It attempts to break down a complicated process and study it sort of one scale at a time. Okay, and for simple enough processes, of course, if you had 10 to the 4 objects all at completely different energies, this approach wouldn't work. But the idea is we can identify simplified observables that are sensitive to only a small number of scales, and we can sort of try to compute one at a time. Okay, and also it has the virtue that the number of possible observables, at least in principle, scales with the energy, right? Because you could look at something like some number of hard processes plus x, and the number of hard objects that you have is going to be increasing with the energy. So it scales well with the energy that you have available. Okay. All right, so let's ask about electroweak factorization, and I was encouraged by the fact I was told, I wasn't here, but that there were arguments about this among the experts, and so it appears that this is not a completely settled thing. So anyway, I'm going to wade in and just make some remarks about this that are more or less just something about my attempts to understand what's going on here. So we'll see if this has any sort of validity or value at all. Okay, so I want to claim that extending this factorization idea to high energy electroweak processes is not at all straightforward. So naively, what do we want to do? Well, we want to replicate the successes of the QCD factorization. So instead of having an initial state hadron, now we want to have, let's say, a muon, a random example, right? And then instead of a final state hadronic jet, we want to have some sort of jet now made out of electroweak objects, right? So this is one of the central things we want to talk about, okay? And so the thing is that here, the left-hand, the case that we understand, both of these objects that we're talking about, the initial state hadron and the hadronic jet, is invariant under the relevant gauge group, which is here the color group, right? Whereas in the electroweak case, neither of these things is electroweak invariant, right? And neither is even a mu plus, mu minus or something. These are all not electroweak invariant, and neither is a jet, okay? And so somehow that makes things different, okay? Now, how does that make things different? Because that's somehow a technical thing, right? Because the point is that, of course, these states make sense, even though they're not gauge invariants, because gauge invariance is broken, right? So, but gauge invariance is broken now. If we're at the PeV scale, we have to think of that as some IR scale, right? That's somehow happening at the bottom of this cascade. So electroweak gauge invariance is broken in the IR. That's why it makes sense to talk about colliding muons rather than SU2 multiplets, and why it makes sense to have, let's say, a Higgs rather than, you know, some gauge invariant thing made out of Higgses in the initial and final states. But in between, in the hard process, unbroken electroweak symmetry is what governs the underlying hard process, right? We want to see the restoration of electroweak symmetry breaking directly before our eyes, and we will if we are allowed to make these colliders. Okay. So let's go back to basics and try to understand why this is a problem, okay, and in some kind of a more principled way. And to me, there are some, well, I'm just going to say, to me, there are some conceptual mysteries that I'm going to try to highlight here. So let's go all the way back to QED. So in QED, the simplest process, whatever it is, chapter 0 of Peskin and Schroeder, we talk about E plus E minus goes to mu plus mu minus. Later on, we learn that there are radiative corrections, okay? And we can calculate them, and we find that they diverge as the logarithm of the photon mass. Okay, so of course the photon mass is 0, or yeah, let's say it's 0. So this is a nonsensical result, right? So the photon mass here is some kind of infrared regulator. All right, and so what is the meaning of this? Well, somehow this was understood even before the renormalization of QED, which I don't understand that, but that's a fact. So Bloch and Nordzig, all the way back in 1937, showed that this problem goes away, okay, if we sum over soft photons in the final state. And this is by now textbook material, right? You can read about this in textbooks. So roughly the idea is that you have to include states with any number of soft photons. You integrate over their phase space, but only with a cap on the total energy carried by the photons. And then everything is finite, right? And this is supposed to be intuitive, because the idea is that states with additional soft photons are indistinguishable, right? Because below some experimental threshold delta that's small enough, we couldn't tell the difference. And so we should be completely happy with this, okay? And small now, of course, is small compared to something like a PeV scale, you know, this unimaginably high scale that we're pretending that we will have colliders at. So yes, exactly. But then in terms of muon into say a neutrino, which looks very different in your detector, right? A W or a Z looks very different, well, maybe not different enough, but as for a theorist, they look completely different.
Put it in the PeV scale, we'll say the W is massive, so
Right, but by the time it gets to your detector, it's a completely different problem. Well, that's somehow the mystery. Somehow the muon or the W or the Z in principle are both partons and hadron. That's the way I would say it.
well, the partons are usually in a bound state. Can you do this on a bound state?
Well, that's the problem. The muon is not, I mean, the problem is the analogy doesn't seem to be that. I can say more about this. Let me ask you, here's a little thought experiment. Suppose the QCD was not asymptotically free. Suppose we have lots and lots of ports. Okay. Perturbation theory looks exactly the same, except some coefficients are different. Okay. But what would you write down here? There are no protons. There's no confinement. Okay. Now, what you would be, you could look at the proofs of factorization, and they would still look like this, but this F would be just.
Well, you're saying the
Are
you saying the quarks aren't confined then? But
so in some ways, I feel like we were helped. The fact that nature gave us confinement. And so we know what the initial states are. We don't know how to compute with them, but we know how to do this factorization. What we're supposed to factorize is very clear because we have hadron. Okay. And just like this would be different if we had pions here or neutrons or even antiprotons, we have different F's. Okay. In a theory where we don't have confinement, we would just have a continuous infinity of possible initial states. And it's not clear that a statement like this is useful. That's a thought experiment. That's not, I know that's not practical. Okay, so maybe I'll go to the second half of my talk, which if this was boring, then my second part of my talk is going to be even more boring, which is, okay, so there's no transition.
Sorry, can I ask you something? So a weak coupling, why you are worried about this constraint of gauge invariant states that you could solve in perturbation theory? Okay, so that's the usual picture, no? That the bare field then is dressed up as it evolves, which amounts to solving your constraint equation in perturbation theory. Why this you think is not satisfactory?
I'm trying to say, I guess maybe to summarize, what I would say is that the QCD factorization theorems are gauge invariant statements, so they make sense. So the fact that we can prove them order by order with perturbation theory is very encouraging. For the case of electrolytic symmetry, I guess another way to say it, my understanding is that our understanding of factorization is almost entirely diagrammatic. Okay, starting with Bloch-Nortzig and continuing these factorization theorems. Okay, and do we need to do better than that? Well, I'm not sure, but at least those statements are gauge invariant statements. Whereas for muon collider, the electroweak gauge symmetry, I don't know what the correct gauge invariant statement is that you're trying to prove. I could be wrong-headed about this, but that's my statement. That's what I'm trying to say. Okay? Yeah. It's okay if I don't get to the second part of my note. I'm fine.
I can say in the first week we had lots of discussions, which partly looked pointless, but maybe they weren't, given what you're saying, on precisely this issue on how to factorize and why in some cases there were big disagreements.
Saw some of these things, and then I just heard that this happened again. So that was partly my inspiration, but I don't have informed opinion.
I'm not grasping your worry about the bias of the initial state. In a sense, will it change anything if instead of applying new Plassmann we collapse you collapse an atom of P plus, E minus with P minus E plus, so there are agents which are gauge invariant.
I think at least at a level of principle, then we would maybe be able to write down, you say, would it change anything? I mean, it seems a much more complicated process, but from a conceptual point of view, it seems better from this point of view, because as you said, then you're at least talking about physical gauge invariant state.
Because from
Well, actually, sorry, muonium or something, sorry, it was a physical, sorry, the problem is, sorry, no, that's wrong, sorry. So let me see. No, the problem is not that there's something wrong, like the experimentalists are doing the wrong thing by colliding muons because they're not gauge invariant. The problem is the way that we, our theorists, are describing it.
if you write that formula for partons, now starting instead of V plus V minus, we start with two analog of partons, right? Which are stimulus under V plus V minus.
Right. Yeah, somehow the point is that muon, so, the initial state muon, here's another way to say it, is Bjorkane, I took a class on perturbation when I was a grad student, and he said, look, colliders are just boosts from the point of view of the theories, right? So an initial state muon, coming into beam, is not collided yet, is just a very boost to muon. I can go to the rest frame, there it is, it's a muon, okay? And I know that somehow with low energies, gauge symmetry is unbroken, and it is broken, so it makes sense to talk about a muon. But when it starts participating in a hard interaction, okay, it somehow realizes that it's a member of this multiplet and can freely turn into neutrinos, can radiate WZs, Higgses, whatever, right? And so we don't know, I think we don't know the right way to describe that. That's what I'm saying. It's both a parton and a hadron. It's a hadron because it is a physical state, even though we don't describe it formally in that way. And rest, and muon rest is a completely gauge invariant state because of electrolyte symmetry breaking. But when it participates in this hard interaction, it's somehow a parton that is part of this multiplet.
I guess it really comes from the fact you are trying to be sensitive to some scale. If you're trying to resolve super small energies, then you get all the problems of soft photons you mentioned. If you try to be sensitive to a super large range of energies with W's, you will have one case you are consistent with being a parton, in the other you would like it to be hadron, and both cannot be at the same time.
Having higher photon resolution, you will start seeing more and more photons according to these formulas, right? So I mean, yes, these divergences, they eventually get cut off by some real infrared effects.
I was just about the analog of a proton is your muon plot, it's cloud documentation stuff. That's the gauge invariant state. Then if you hit the high energy, you'll only see a little bit of it, but if you hit the low energy, you'll see the whole thing. So presumably that means the low energy interactions, it behaves gauge invariant, and the high energy interactions, this is a kind of part of distribution.
Yeah, I think somehow what we want to do is we want to find the probability of finding a muon parton on each side of the muon, right? And that's what people are doing in practice with diagrammatic types of arguments, okay? But I believe that there are some things, and I would like to understand better what puzzles are. I'm very grateful if somebody could invite me about that. But I think we don't even quite know how to formulate. As I said, in gauge invariant way. I do know how to formulate a muon mass. So how do I don't know.
Yeah, presumably it would include virtual W's and Z's in the distribution as well, just like the proton includes gluons in there.
Right. Exactly. I completely agree. I got that far. I didn't put it in my slide, but I did get that far.
So then just use perturbation theory from that on. You start with the gauge invariant operator, produce a gauge invariant state up to U1. Yeah. Yes.
So, yeah. So somehow I agree. It should be something like that. I agree. So maybe, as I said, maybe what I'm saying is no.
But just to complete, if you put your hands on a calculation, it turns out, at least in my experience, and maybe others may disagree, that the domain in which you normally can have things under control, so that formula makes sense because in practice you see things converging, like there is no such effect that you add an extra radiation and things blow in your face. It's a lot more narrow than what happens in QCD with extra jets or in QED. So, and honestly, I don't think I have a clear intuition on how should I have known ahead of time that this thing was exploding right there, where in QCD or in QED things seems to be better under control. Maybe it's just a chance, maybe it's connected to what you said. Honestly, I admit I don't understand it well enough. Maybe it's just a chance again.
I believe that all of the progress in understanding this question has come from this diagrammatic point of view, rather from some sort of first principles, more first principle kind of thing. So I'm just saying that the first principles questions are still interesting to me. Okay, and
there are definitions
of
initial
final states which have gauge charges in a non-perturbative definitions, right? In axiomatic quantum field theory, which involve like lines of the gauge field that go to infinity and don't close, and so basically you need to dress your field with the. And I think this exists both for QED and then has been generalized also to non-abelian theories.
I'm pretty convinced that those, at least specifically, are completely bullshit. And so we can talk about this, okay, but I don't want to talk about that now. Okay, I'm going to just leave that. Very too exciting. Yeah. So anyway, that's something I don't think is the right proof. Okay, but that's something that is an attempt exactly. I think.
So I agree. I mean, there is nothing that you can infer about factorization from those definitions because.
Time ago, by God Salam, apparently his advisor had him thinking about, generalizing Pinea-Coolidge type things in perturbative QCD. He got nowhere, and in this talk he said, like every 5 years or so, he gets this thought that he should think about it, and then he just wastes, a month of time or something, and goes on and does the more practical thing. So, yeah, I think there's a recognition that there is something in principle to be understood, but not that it may very well be useless. Certainly, it hasn't been shown to be useful for any practical calculation. So, should I stop? I mean, I'm happy to stop.
You can stop and we would be just basically debate, but if you want to quickly.
I'll just tell you what the second part of my talk is why the standard model is not boring. Okay, and I really believe this. I'll just go through this first slide and you'll get enough of the ideas that maybe you'll be okay. But, I'll just let it after this just be a question. Okay, so.
No conclusion. All right.
This was the guy that he really wanted to have this talk, and this was the right quote with it, right? That, look, the universe is not some generic thing, we should be happy with it.
No boring metal.
You know, he's happy with the universe is not. I think it's good. You talk crappy.
Okay, no microphone, don't worry. So we had already discussion and probably coffee for once we can go slightly on time. But if there is a quick urgent comment you don't want to bring to coffee because you want everybody to hear, then that's the last chance. Otherwise, you can have private conversation now at the coffee. Thank you, Markus.
Thanks.